Okay. Let's see. We got water bottles 2, medium. You're given 2 integers, num bottles, and num exchange. Num bottles represents the number of water bottles that you initially have, and one operation can perform one of the following operations. Interesting phrasing of it. Drink any number of water bottles, turn them into empty water bottles, exchange num empty bottles with one water bottle, full water bottle. Then increase num exchange by 1. Note that you cannot exchange multiple batches of empty bottles for the same value of num exchange. For example, if num bottles equals 3 and num exchange equals 1, you cannot exchange 3 empty water bottles for 3 full. So it's 1 at a time. Okay. Determine the maximum number of water bottles you can drink. So if you start with 13, the exchange rate is 6. Drink 13, there's 13 empty water bottles. You exchange 6 and 7. You exchange 6, yeah, you exchange 6 and 7, that means you get 2 full back. Drink 2 more. Exchange rate's 8, so that's as most as you can. So 13 plus 2. Seems simple enough. Unless there's some faster speed than just actually doing it. The num bottles is quite small. Alright, I'll do the simulation and see if it's fast enough. So I think I need to have filled and empty is going to be num bottles and 0, while what's the stopping point? While filled plus empty is less than what is the stopping point? Stopping point is when your empty water bottles is less than the num exchange. No, that's not right because that's the initial condition. Maybe you just need to actually start with emptying everything. So maybe you actually start with filled is 0, empty is num bottles, assuming that you drank all the bottles that you could. Okay. Let's see if that, well, empty is greater than greater than or equal to num exchange. Doesn't feel right. Let's keep going. So given I have some exchange rate and some number of empties, like I have 100 empties, exchange rate is like 5. Don't want to manually do each one, like subtract 5, subtract 6, subtract 7. It just seems a little slow. Okay, this is an example. So let's say I have empties 100. Exchange rate is, say, 5. So it'd be like 5 plus 6 plus 7 plus dot dot dot. some number, let's say m for max, is less than or equal to 100. So I guess I need to know m, and then if I know what m is, then like m minus 5 is roughly the number of exchanges. How do I do this? So the sum of a sequence that is increasing like this is, I think, the a1 plus a n over 2. No, a1 plus an times n over 2, I think. a1 over an divided by 2 is the average times the number of numbers. So that should be like 5 plus m divided by 2 times m minus 5 plus 1. If you include, it goes 5 to 6, that's 2 numbers, so it's like 6 minus 5 plus 1, so it's 2. It's less than 100. So if I multiply by 2 each side, 5 plus m times m minus 4 is less than or equal to 200, and then that's quadratic. Oh boy, oh boy. Is in fact quadratic. Oh. Wonder. I wonder. 3, 4, 5, 6. I mean, the most it could possibly do is, if it increases at 1, it can cap out at the number of full bottles, I guess. Right? Because if the number of full bottles, if the number of bottles is, let's say, 10, you can never exchange past 10. How did this thing actually stop? So 10 empties, and then you exchange 10. I see. So when you make that exchange from 10, the exchange rate actually reduces the total number of bottles by 1 less than the exchange. Like you move out the exchange and you get back 1, so it's like, yeah. So 10 goes down by 2, that gives you 8. 8 goes down by 3, that gives you 5. 5 goes down by 4, that gives you 1. And then 1 is donezo. So you have 10 minus 2 is 8. 8 minus 3 is 4. 5. 5 minus 4 is 1. And I guess the number of times you did that, the number of times you made an exchange, you got one more bottle to drink. So 10 plus 3 is 13. Okay, so this one, 13 minus 6 is, no, 13 minus 5 is 8. 8 minus 6 is 2. Then you can't do any more exchanges, so it's 13 plus 2. Okay, so it's the number of water bottles plus the number of times that you can actually do an exchange. Where the number of exchanges is just an increasing, it's just how many numbers from num exchange minus 1 to that number. Okay. I think then maybe I can actually do answer equals num bottles to start with, and then while num bottles is greater than num exchange, num bottles is subtracted by num exchange minus 1 answer increments. I think this should be less greater than or equal to, and then num exchange increments. I think that might be it. Okay. So there's something slightly faster, maybe. Something slightly faster. Well, implementing 1 each time here. Implementing 1 each time. Well, num bottles greater than or equal to num exchange, num bottles decrements. I think maybe I can do something like I just did something like remove this and maybe have an original exchange. And then the answer is equal to I guess I want to store both the original exchange and the original number bottles. And the answer is just the original number of bottles plus the num exchange that ends up with minus the original exchange. I think that's right. Well, I guess I don't need the parentheses, but can I even combine these two somehow? I don't know if I want to. It's, logic there is like okay, I think this is good enough. Okay. So summary is the math to quickly calculate the number of water bottles that can be drunk is equal to the number of filled water bottles at start, and the number plus the total number of exchanges done, as each exchange gives one more water bottle to drink. One more filled water bottle to drink. This can be simulated in the loop above, where num bottles decreases by exchange rate -1. Since, like, example, rate is 3, give 3, get 1, so down 2 bottles. It's going to be similar for number of 1 and count and exchange rate increments. Slight optimization to quickly calculate the total number of increments or exchanges as difference of final exchange rate and original exchange rate. Okay. Time complexity, this can be O of this is O. Yesterday I said it was O log of n, but maybe it's wrong. Because this thing seems like it'd be slower than log n. The number of times you do the loop is quadratic, roughly. No, it's the square root of n, I think. I think it's the square root of n. Is the square root of n faster or slower than log n? I think the square root of n is slower than log n. Gut feel is it's O of square root of n. Since the number of loops is based on solving a quadratic. Yeah, so if your exchange rate is like 3 and your number of bottles is 100, it's 3 plus 4 plus 5 plus 6. Yeah. It doesn't. However, my last problem with one from yesterday was I thought was O of log n, but that would be faster than this, and this seems like it should be slower. Log n is, yeah, log of 100 is like 2, and log of square root of 100 is, or log of 100 is 2, and like square root of 100 is 10. I guess maybe there was a different calculation in the last one. Never mind. I think maybe, I feel like maybe, no. Okay. Space complexity, this can be O of 1, since no extra data structure was needed. Okay, cool beans. One of the simpler medium